You're on.
Hi everyone, I'm Jewett, and this is the ethics controller. Alright, so basically middle class problems. In today's world, you have a lot of different digital devices. A lot of them will run off from an IR device or an IR transmitter receiver combination, which stands for infrared. And let's see, so being surrounded by all these different electronics, having a pile of remotes to have to remember what controls what can be pretty difficult for some people to do. Java, no thank you. Stop it!
Want to start over?
So, the dilemma. Okay. Let's see. So I decided to create a controller that could solve this problem, or at least try to solve it the best way possible. So really, for this issue, trainability was the key, because when you have a remote, or when you have all these different signals bouncing around, you want this one remote that's going to solve the problem to be able to learn all your different remotes that are in your house that will be running on the same bandwidth. The bandwidth I'll talk about later. So basically my goal for this project was to simplify and improve quality of life for people in middle class. America, give or take, maybe Europe, we'll see. So what's going on here? Basically we have a bunch of different remotes controlling a bunch of different things that really just makes things confusing, especially for old people. Let's see, so the majority of the devices are all using this single signal type, or bandwidth, and that's what's going to make this project pretty much doable. The remote will use a signal and potentially, or we use this signal type and potentially be adjustable, depending on how difficult they get, or how complicated the circuitry needs to be. So my system diagram, basically what's going on here is we have several different controllers. This is my system right here. So what I was really hoping for here was a freedom-based design, or freedom board-based design, so it had the ability to control several different things at once, different components. So, say for instance, the signal coming from each of these remotes is going into the receiver circuitry, and then that signal is being stored or in the memory of the freedom board. The keypad is what you use to access that signal, and also it's what you're going to be using to store each of those signals. The LCD will tell you what mode you're in, so theoretically different manufacturers might have a different bandwidth outside of this general bandwidth, and the LCD will tell you what mode you're in. It'll tell you, potentially it could go in more depth and tell you how, what bandwidth it is, potentially what buttons being pressed if the number system on the keypad doesn't match necessarily. And then once you send the signal with the keypad, or tell the board to send the signal with the keypad, it's sent through the transmitter circuitry back out to the devices that these individual remotes control. So let's see here. Alright, so the main concepts and components of my project, as I mentioned earlier, are the LCD, the keypad, the freedom board, and my receiver transmitter circuitry. The receiver transmitter circuitry is fairly basic, and it really doesn't require all that much, all that many different components to make it work. Basically, it's just you have your connection to your microcontroller, which is the freedom board. In this case, you have your transmitter diode going through, or with a resistor to limit the current, going to ground. And then you have coming in from your 5-volt source, potentially from your Freedom board, because that has a 5 to 9 volt or 3 to 9 volt power supply on it. And basically, what it's going to be doing is feeding the power to the receiving transistor. The transistor will receive the signal from the diode, or from the transmitter diode, or photodiode, and then that signal will send a high to the, or low signal to the, back into the Kinetis board, and that's where it can be stored. So basically this one remote is going to, the difference between this controller and a regular controller off the shelf is that it has the circuitry of the device that is receiving it and the device that's transmitting. So it's almost like a combination of the TV and the remote in one. And so let's see, next slide. So this is what I call the butter zone. Basically, I built my board for the 38K or kilohertz bandwidth, because that's the most commonly used bandwidth in the marketplace today. So now, essentially what we have in this image here is a breakdown of what the transmitted signal is versus what the signal that the TV is, or the TV, or in this case it'll be my controller, is breaking down and coding into its memory. So there's a modulated signal and a non-modulated signal. So the the remote, or from the photodiode, is the non-modulated or is the demodulated signal. So it basically is several bursts of 38K, or of a 38,000 hertz frequency, broken up into bunches where it looks high and low. So that's why when it goes through the receiving transistor, it will will modulate that signal and make it bursts of high and low. And this signal almost resembles like a barcode that you would see off from anything you buy from a store. And generally it'll repeat the signal. It'll be bursts of the signal with repeated signal in case there's like an issue with transmitting. So the receiver will know that for that one burst it received this signal, and it'll essentially ensure that it gets there. And this is a signal that I actually captured from the circuitry that I built in the previous slide. It's showing the modulated signal, and if you were to break this down further and further, you would notice that it actually shows the 38,000 hertz individual pulses. So let's see. This is a circuit that I am in the process of completing. It's based off from, it may look familiar to the people who are in microcomputer technologies. It's the add-on board that we built for our Freedom board last semester, but it's got a little bit of modification to it. I basically gutted the circuit, left the same format, but left some of the components that were still necessary for the circuitry to run, and I adjusted a couple things around. So basically, it's got the transmitter circuit already in it. I found when I was going through the initial circuitry of it, I found a receiver circuit that was already, in there, but it was for not an optic. Anyway, it was for a photo receiver. And so it was a similar principle, but I needed a little bit of adaptation as well. And so that way it would be able to fit, instead of being a 2-pin photodiode, it's actually a 3-pin photodiode transistor combination. But anyway, So with that circuitry involved in it, I was actually able, will actually be able to receive and transmit signals, store them to the Freedom board, which is going to be connected into these pins. The LCD takeoff is right here, and the keypad takeoff would be right here. And this is how it's going to be powered. I'm actually using a voltage regulator in order to limit the voltage coming in from here, because it's going to be too high for the LCD. So because we're using a 9-volt battery instead of the traditional 3 AA setup, in order to get a high enough voltage going in to get full contrast on the LCD. And so it's not finished yet, but basically the idea of the circuit's there and the main components are, but I haven't gotten it to a hot 100% route, and but it's a work in progress. That is the end of my presentation. If anyone has any questions, feel free to ask them.
You were talking about the voltage regulator. It's not on the board, right?
Right.
Yeah. Okay.
Yeah, I just have to put in a 3-pin or a 3-terminal device, and then assign the pins for it to basically pick up from the the V in, tie the excess to ground, and then the outward pin will tie into the power for the board.
The 3-pin photo receiver you have, is that shown here?
No, I actually took off because there's the 2-pin photo receiver would be actually right here. I had a 3-pin, there was 3-pin terminals on here before that I was gonna connect into it, but I accidentally removed them, so I have to put them back in.
Okay.
And replace this with that and connect it in a necessary way. But
so, is that what you do have there? Is that the photo receiver, or is that the sender?
that's the receiver.
Not the transmitter?
This would
3-pin device was the receiver.
mine was a 3-pin receiving device, but this is a 2-pin receiving device that was on there.
Okay. This is a pin diagonal.
Right.
Okay. If you go back a slide.
Yeah.
The waveform. So, how much time is being shown in that oscilloscope shot?
10 milliseconds per division.
So it's 60 or 70, right?
Right.
Did you say what that represents? Is that like pushing the up button, down button?
That was pushing the power button.
Power button, okay. And
So I didn't mention that. That was the power on.
So 60, 70 milliseconds is not at all related to the 38 kilohertz, right? What is, if you...
I broke that down.
Well, you said you could see the 38 kilohertz in here, but I can't see
Well, apparently, what it's supposed to be is basically when you break this down into smaller components, this is the entire signal.
Mm-hmm.
So when it's broken down into its modulated or demodulated form, it will it will basically be these blocks of high will be independent 38 kilohertz pulses, and then in the down zone or in the low zones, it would be a absence of the 38K pulse.
Isn't that what's being shown in the upper diagram?
Yes.
The little pulses, aren't those
Yeah,
38?
that's
Okay.
the 38K.
So if you were to draw with a marker along the top of those little pulses,
Yes.
and then go down into the valley, the long wide valley there,
Right.
and then follow the top of the pulses again, isn't that the modulated signal that you see in the lower one?
Right.
Okay, so I think you're right. So, so what it means, because if you do the math, 1 over 38 kilohertz is something like 27 microseconds. Right?
So it's actually, this is actually a lot larger.
This is huge, yeah.
Yeah.
So what's really happening is there are hundreds and hundreds of the 38 kilohertz pulses wherever it's high there.
Right.
Okay, and the if you want to think of it as an envelope that encloses those peaks,
And just sends a high
Is what
signal as
you're-
a modulated signal.
that envelope represents the high.
Right.
And your little 3-pin device is looking at the pulses you see in the top diagram,
Right.
but converting it for you, essentially filtering it for you to produce the diagram at the bottom.
Right.
Okay? So,
Because the pin diode wouldn't filter that
Exactly.
that
So
circuit or the signal, and it would just show the demodulated signal.
right,
Yeah.
well, this is the demodulated, so it would show the
This is-
undemodulated.
Yeah. This would be the modulated signal. This is demodulated. I think. Oh wait, no. I'm getting these backwards. Demodulated, modulated. Yeah, that makes sense.
Well, you have it labeled in the middle. The modulated
Yeah,
signal
that's
is
the
in middle,
modulated
right?
signal that's going
So
from that.
Yeah, so the modulated signal has the overall shape of the data you're trying to transmit, but it's being created out of these 38 kilohertz
Right.
pulses. And I just wanted you to explain that better about how, because you got two diagrams
Right.
that are not at all consistent with each other. So if you're gonna label that upper one, each of those little pulses would be like 25, 27 microseconds apart, those little blue pulses.
Right.
And there's, you know, you can do the math, there's 27 into 10, because it's like 10 milliseconds for that first pulse in the lower diagram.
Right.
So there's 50 or so of the 38 kilohertz pulses in there.
Right.
Yeah. All right.
Any other questions?
So when do you think you're gonna be able to pull a board together in the next
Yeah,
days?
I think that that's possible.
And your goal is at least to get one key trained and be able to
Right.
demonstrate you can send that. That would be good.
Receive and transmit, or receive, save it in memory, be able to retransmit
So
it
yeah,
and have
but use
action.
your freedom board, push a button on that keypad, and
Right.
it will turn something on.
Right.
All right, that's a good goal. Other questions? All right, thank you.
Gentlemen in the back?
Oh.